So let's discuss notion of the limit of a function. Now say here we have f, a real valued function, and say it's defined on the entire real line, and we are interested in discussing its limit at 2. Okay, so notice this: as the x values approach 2, the function values approach what? The value 1. And here we say that the limit of this function as x approaches 2 equals 1. So let's discuss this phenomena in an analytic fashion. Now here is a way to describe the statement that the limit of this function is 1 as x goes to 2, is that we can bring the values of the function as close to 1 as we please by keeping the x values sufficiently close to 2 but not equal to 2. So notice this here. This stripe that you see here, they are the y values in the vicinity of 1. And if we want to say it like more clearly, then it will be that the distance of these points from the value 1 is no more than 0.2. Okay, so let's come down here graphically, okay, and go to x values. All right, so here we are. Now notice what happens if we stay, or if we keep the x values in this interval around 2, and we may choose to ignore 2. Actually, yeah, right, we are avoiding taking it equal to 2 here. So for all these x values, what we will have, the function values will be in this interval containing 1 to the level of our desired accuracy. That is, we didn't want the function values to be farther from 1 by more than 0.2 units. Okay, so I'm going to show you another illustration with the same example. In general terms, if we consider a real valued function that is defined on an interval containing a, except maybe not at a, then we say that its limit at a equals L, or the function approaches L as x approaches a, if we can bring the values of f as close to L as we please by keeping or bringing x sufficiently close to a but not equal to a. So let me take a different example, as I said in the last one. Now let's consider a function for which we have the expression given here, and say we take the function sine x over x, and this function has as its domain the entire set of real numbers except 0. So let's investigate its behavior near 0, because if x is not 0, the function is well defined, and you saw that how we compute such limits using the limit properties, but here we are just looking at more precise definition of limit. So now let's look at sine x over x, that function with numerical values. I'm using this spreadsheet to create the numerical values. You can use the table feature of your graphing calculator, and we're interested in near the value 0. So how about we just stay within negative 0.2 to 2, and we may go in the steps of 0.01. Okay, so we will go ahead and get the whole thing, and we may stop at say 0.2. Okay, well, here nothing wrong in stopping at 0.21 anyways. So here we have sine of x divided by x, and there we are. So first of all, we did not remove 0 from here, and it is pretty gentle in just telling us that division by 0 is not allowed. We should have deleted it before, but anyways, let's delete it now. And we have a pretty good idea here that as x goes to 0, the function values appear to approach which value? 1. Later I shall post a deductive proof of this for you, but right now let's stick to this numerical approach. Okay, so what we have is that as x approaches 0, sine x over x approaches 1, and let's look at it in terms of our previous formulation, okay, that we had. So here, let me insert a scatter plot here for you. Okay, so here we are. So we have sine x over x, and graphed like this. All right, and we have as x approaches 0 from either sides, the function values are approaching 1, and we can do this, take negative 0.2 and say negative 0.199, and we can see a denser graph. All right, so let's go ahead and discuss it. So in this case, here we have the function values and here we have the x values. And let's say that we want the values of the function to be no farther than 0.001 from 1. So that means that we do not want to let these go above this, which they're not doing anyways, and not below this value. So how do we accomplish that? We can accomplish that by keeping the x values within this range. All right, okay, so that means that if we kept our x values on the right of this and on the left of this point, okay, and not let it land at 0, then the function values will be no farther than 0.001 from the value 1. Now notice this, that the value of the function is in this interval. That means what? That can also be stated as that the distance of fx from what? From 1, which is our L value, okay, is no more than how much? 0.001, or staying within this interval can also be written as, remember, for the distance between fx and 1, we can use absolute values, that which we use to define distance along a real line. So staying in here means what? That the absolute value of the difference between fx and 1 is what? Less than 0.001. That means, we wanted to keep our function within what? Within this much distance from this value 1. And we are going to discuss that how can we handle the x values, or how can we keep our x values so that the functional values stay within those bounds. Okay, so these are our bounds for the x values, right? So we will go from here up to here, and of course not at 0, right? And the same thing here. And how much is this value? We are not able to read it exactly over here, but this is 0.05, 0.06, 0.07 might be a little safer estimate for that. We can look into our spreadsheet if we want. Okay, I had gone ahead and then had taken it like through the smaller value, so 0.07, and that is within that limit. Okay, so anyways, as we were visually correct here, so here this value is what? this is like 0.07 here, and negative 0.07 in this part. So that means if we kept, or if we took x between negative 0.7 and positive 0.7 and avoiding the value 0, then the function values will stay close enough to 1, as close as we wanted. So that means what? Here, let's describe the behavior of our x values over here. So here we have x. Okay, now we are looking at the distance of x from 0. Okay, and I'll write it in little formal fashion. That is absolute value of x minus 0. Okay, and so what we have here for these values, that is less than how much? 0.07. Okay, now we also have to stress that our x value cannot be 0. So we can do this. We can just insert this statement that 0 has to be less than that, and that statement then tells us that our x cannot be 0. So what did we accomplish here? That if we have this x value according to this statement, then what will this imply? This implies that the fx values, or the function values, are going to be within this range. Okay, so this was our desired proximity near L, or the limit value, and for that we have to be what? We have to be this close to the value a, which is 0 in this case, and of course this is stressing that x cannot be 0. Okay, now here I made the graph denser to just look at another viewpoint. That is, say, instead of keeping our distance from 1 as 0.001, say we wanted to get closer. Okay, that is, we didn't want our distance to be more than 0.005, which means that we would like our fx minus 1, the absolute value, to be lower than how much? 0.005 instead of 0.0005, I'm sorry, instead of 0.001 as we did previously. So what we will have to do in this case is that let's go down here. Okay, and let's go down here. All right, so I mean, this will be hard to read here. We may go back to a spreadsheet, or unless necessary, we may just read these values here. That is, .52, and here this is negative 0.05 to 0.05 is enough. Or in other words, if we have 0 less than, and again I'm just writing it formally, that is 0 less than absolute value of x minus 0, and that being less than 0.05, what will it imply? It will imply that our function values will be what? Desirably close to 1. Okay, so this is so we are going to go ahead and formulate it in a little bit more abstract fashion and look at that through a different example. So now let's consider a different function, which is this function's defined by x times sine 1 over x. And here what we have is that our x is what? Our x is different from 0, and of course it's not defined at 0, and it is defined everywhere else along the real line. Now here is a graph of this function. You can generate this graph by using your calculator, and notice this: as x approaches 0, the function also approaches 0. So let's discuss this in terms of the formulation in which we discussed our earlier functions. So for this function, x times sine 1 over x, where x is not equal to 0, what we saw is that the limit of this function as x goes to 0 is 0. Now let's see if, as in our earlier situation, we wanted that our function should be, say, no farther than, let's take a number, a small number, say 0.001 units from the limit, then how should we confine x near 0 for this desired proximity? So let's do these calculations step by step, and sometimes it takes a little practice to get good at it. So we have fx as x sine 1 over x, and of course I already subtracted 0. And now we will do a little analysis. That is, notice this: sine 1 over x, or sine of any quantity, is always less than or equal to 1. So what we have is that this product is x times a quantity which is always less than or equal to 1. So if we took this only, that is x less than 0.001, this product will have to be less than 0.001. And what has happened here? We have this, that this number and this number, they are about identical, and which is not really that big a surprise, because you can see that both these graphs are like bounded by these y equals x and y equals negative x. I am just sorry about that. I'm just graphing it just very approximately. Okay, so in this case what we have, that say we took our desired proximity near the limit for the function as 0.001, then in that case the corresponding number for x values also turned out to be 0.001. Now let's go ahead and get a little more formal. So remember, in our earlier examples, we set a desired proximity level near the limit L, and for that we found how close we will have to be near A, or how close the x values have to be near A. So 0.001, one of the distances turned out to be 0.07, and say if we took it as 0.005, 0.05 appeared to work. So when we generalize it, then what we do is, first of all, let's go for a terminology. For the distance of the function from the limit, here we took it as 0.001, here 0.0005, and in other cases we took some other values. So let's go ahead and take a symbol that is very widely used. So this distance this number that we use for distance from the limit is generally denoted by this Greek letter called epsilon. Okay, so that is what it is called, and that's an approach that you shall see at many places. Okay, and for the distance for the x values from A, the value that is the symbol that is generally used is called delta. So what we do is that once we specify our epsilon, we wanted to ensure that we can find delta in case that limit statement is true. Okay, So let's go back to our statement in the beginning. That is for a real valued function f that is defined on an interval containing a, except possibly at a. We say that limit of the function at a is L if for any epsilon greater than 0, okay, because the distance has to be positive, okay. All right, we can find delta greater than 0, because again we are using this for distance, okay, such that what we have is that the value of the function, or the distance between the value of the function from L, the limit, is less than epsilon if we have what, 0 less than x minus absolute value of x minus a, and that has to be less than delta. That is, we can bring this function values desirably close to L by taking the x values sufficiently close to a, and of course not equal to a. Okay, so let's realize this through a very simple example. So say we are given this function 4x minus 3, and we have to show that the limit of this function at 2 equals how much? 5. So that means what? No matter what the value of epsilon is, we should be able to find a delta for that value. So so that this highlighted statement is fulfilled. So what is our fx in this case? Our fx is 4x minus 3. Our L is how much? 5. And well, I don't know why I erased it. And we have to do this. We have to find that, we have to see that how close do we have to have x to 2, okay, so that this statement is satisfied. Okay, so we will do this. Go ahead and simplify it. So this happens if what? This happens, that is, we just plainly simplified it. Or if what you have, we go on simplifying it, and hopefully we will have a result. But keep this in mind that most of the times it would not be as simple, and in those cases we shall use some other methods. So anyways, so or if this, and then what we have is we can factor 4 out, okay, 4 being a positive number, and then we can do what? We can divide by 4 and still preserve the inequality, because 4 is a positive number. So when we do that, what shall we have? X minus 2, that is less than how much? Epsilon over 4. So delta for this purpose, this value delta has come out to be how much? Epsilon over 4. And we can choose x to be not equal to 2, and still this statement will be satisfied. Okay, so go ahead and read the section and read the other examples that I have posted, and if this is not clear, let me know and I shall try to explain again. Okay.